Welcome to a deep dive into gradient descent. It's well, it's a really fundamental concept when it comes to machine learning, and today we're going to try to break it down for you, even if you're totally new to algorithms and models and all that stuff.
Absolutely. Yeah, we're going to explore we'll explore what it is, why it's so important for, training all these machine learning models that you hear about, and just some key things to know about how it works.
Okay, perfect. So first things first, what exactly is gradient descent? I mean, I've heard people use the term like optimization algorithm, but what does that actually mean, like practically?
So imagine you're trying to build one of these machine learning models. You want to predict, let's say, house prices. You've got, data about different houses, like their size, their location, number of bedrooms, and you want to create a model that can like actually estimate the price of a new house, based on these features that you have.
Right. So it's almost like we're finding a formula that connects all those features to the price.
Exactly. Yeah, that's a great way to think about it. And that's where gradient descent comes in. It's this algorithm that helps us find the best values for the parameters of our model. These are the numbers that determine the relationship between those features and the price. The actual price.
So it's like we're fine-tuning the knobs and dials on our model.
Yeah.
To get the most accurate predictions.
Precisely. Yeah. You can think of it like that. So gradient descent starts with an initial guess for the parameters, and then iteratively it adjusts them to try to minimize the error in the model's predictions.
Iteratively. So it just keeps making these little adjustments until it finds the best values.
That's the idea. It's taking a series of like small steps,
Yeah.
towards the best possible solution. And the way it figures out which direction to take these steps, it uses what's called a cost function.
Okay, so what's a cost function?
So basically, it's a measure of how well our model is actually, doing its job. It tells us how far off our predictions are from the real, like the actual prices in our training data. The lower the cost, the better our model is performing.
Oh, okay, I see. So gradient descent is trying to find the parameters that give us the lowest possible cost, which means the most accurate predictions.
Yeah, exactly. And it uses something called the gradient to figure out which direction to adjust the parameters in. You can kind of, picture it like as the slope of the terrain. So gradient descent always moves in the direction of the steepest descent, trying to reach the lowest point in that cost function landscape.
Okay, I'm starting to get the picture.
Yeah. But
how does it know how big of a step to take, like how far to go in a particular direction?
That's where the learning rate comes in. It's a hyperparameter, that controls the size of those steps. If the learning rate is too small, the algorithm will take tiny steps, and it'll take forever to reach the optimal solution.
And if it's too big?
If it's too big, then it might overshoot that optimal point and just end up, bouncing around, never quite converging.
So finding the right learning rate is crucial then for efficient, effective training.
Absolutely, yeah. It's a bit of an art and often involves some experimentation to find that sweet spot.
Okay, so we've got gradient descent, and it's navigating this landscape. It's trying to find the best parameters for our model. But are there any potential like roadblocks along the way, like things that could trip it up?
Yeah, so there are a few challenges that can come up. One is getting stuck in what's called a local minimum. You can think of it as finding a valley.
Yeah.
That seems like the lowest point around, but there's actually an even deeper valley somewhere else.
So even though the algorithm thinks it's found the best solution, it might have just found like a decent one.
That's right. Yeah, there are techniques to try to overcome this, but it's something to be aware of.
Okay, that makes sense. What other challenges are there?
Another issue is what are known as vanishing gradients and exploding gradients. These relate to how the gradient is calculated and propagated like through the layers of a neural network.
Layers of a neural network.
Right. So think of a neural network as a kind of like complex model with multiple layers of like interconnected nodes, each one performing a specific calculation. So gradient descent is used to adjust like the parameters of these nodes. But sometimes the gradient can become super small or very large as it moves through the layers.
And that causes problems.
Exactly. Yeah. So vanishing gradients, those can cause the learning process to just slow down, to a crawl, because the updates to the parameters become like minuscule. And then exploding gradients, well, those can make the whole training process unstable and prevent the model from converging.
Sounds like those are some pretty tricky situations. Are there ways to deal with them?
Luckily, yes. Yeah. Techniques like weight regularization and gradient clipping and batch normalization, these can all help to, mitigate these issues and keep the training process, running smoothly.
Wow, it's amazing how there are like all these tools and techniques to kind of overcome these challenges. It really highlights, the complexity, the sophistication of this whole process.
It definitely is a complex field, but hopefully we've laid a good foundation for understanding the basics of gradient descent and how it works.
Yeah, I think we have. So just to kind of recap for our listener, we've learned that gradient descent is an optimization algorithm, and it's trying to find the best parameters for a machine learning model, and it does that by minimizing a cost function.
Right. Yes.
And it does this by iteratively adjusting those parameters, taking steps in the direction of the stinkest descent, and the size of each step is determined by the learning rate.
That's right. Yeah. And we also touched upon some of those challenges that can come up, during training, like getting stuck in those local minima and encountering those vanishing or exploding gradients. But remember, there are techniques and tools available to address these issues and ensure efficient and effective, model training.
Okay, this has been a really, really great overview of gradient descent, and in the next part we'll delve into some of the different flavors of this algorithm and how they kind of approach that optimization process.
Sounds good. Looking forward to it.
Welcome back.
Yeah.
So we've talked about gradient descent. It's a powerful tool, and it helps us train these machine learning models. But it turned out that there isn't just one type of gradient descent. Like there are several variations out there, each with like their own kind of strengths and weaknesses.
That's right. Yeah. It's like you've got a toolbox with all these different screwdrivers. Each one's suited for particular type of screw. So choosing the right like gradient descent variant, it can really make a big difference in how efficient and how effective your model training is going to be.
Okay, so let's kind of dive into these different quote unquote flavors of gradient descent. Where should we even start?
So, well, the most basic form, it's called batch gradient descent, and this is the like classic the classic approach where you use the entire data set to calculate the gradient at each step.
So it's like we're taking this really thorough, deliberate approach, considering all the data before we even make a move.
Exactly. Yeah. And that thoroughness, it can be an advantage because it ensures that each step is taken in the like most accurate direction. However, it can also be a drawback because it can be super slow, especially if you're working with one of these massive data sets.
That makes sense. Yeah, if you have to like analyze all of the data before taking each step, it's going to take a while. So what's the faster alternative?
That's where stochastic gradient descent or SGD, as it's commonly called, that's where that comes in. So instead of using the entire data set, SGD calculates the gradient using just one data point at a time.
Wow. That's a huge difference. So it's much faster then.
Yeah.
But is it less accurate?
It can be, yeah, because it's only using one data point at a time. The steps it takes, they can be more like erratic, and it might not always converge to the optimal solution. But in practice, SGD actually often works like surprisingly well, especially for large data sets.
So it's a bit of a trade-off then, speed versus accuracy.
Exactly, yeah. And that's where mini batch gradient descent comes in. It's kind of a compromise between those two.
Mini batch, so it's like a smaller version of batch gradient descent.
You could say that, yeah. So mini batch gradient descent, it uses a small batch of data points, typically somewhere between 10 and 1,000, to calculate the gradient at each step. So this allows it to kind of strike a balance between the accuracy of batch gradient descent and the speed of stochastic gradient descent.
It's like finding that Goldilocks solution, not too slow, not too erratic, but just right.
Precisely, yeah. And in fact, mini batch gradient descent has become the most popular variant for training many types of of machine learning models, especially these deep neural networks.
Interesting. So we've got the three main kind of variations: batch, stochastic, and mini batch. Are there other like important members of the gradient descent kind of family?
There are, and they kind of build upon these core concepts to address like specific challenges or to improve the performance in different ways. For example, momentum-based gradient descent that adds a momentum term to the update rule.
Momentum, like a ball rolling down a hill.
Exactly. Yeah. It considers the direction of like previous updates. And it accelerates the descent in consistent directions, which can help to speed up the convergence and overcome some of the oscillations that can occur with SGD.
So it's like we're adding a little bit of inertia to the process.
That's a good way to think about it. Yeah. And then there are algorithms like Adagrod and ARMSprop and Atom, which adapt the learning rate for each parameter, like individually.
Adaptive learning rates, that sounds pretty sophisticated.
It is. Yeah. These algorithms, they monitor the history of gradient updates for each parameter and adjust the learning rate accordingly. So this can make the descent, even smoother and more efficient, especially when we're dealing with parameters that have, different frequencies of updates.
Wow, it seems like there's a whole world of, gradient descent variations out there.
Yeah.
Each kind of tailored for different, situations. How do you even know which one to choose?
Well, it depends on a number of factors, including, the size of your data set, the complexity of your model, and the desired, level of accuracy and speed that you're going for. So often it involves, a bit of trial and error to see which variant actually works best for a particular problem.
So it's a combination of, understanding the theory, but also experimenting in practice.
Exactly. Yeah. And as you gain more experience with machine learning, you'll develop a kind of an intuition, for which gradient descent variants are likely to be most effective for different, types of models and data sets.
This has been really, really fascinating, exploring this gradient descent family. It's amazing to see how these variations, they kind of build upon the basic concept to create such a diverse and powerful set of tools.
Absolutely, yeah, and it's a testament to the ingenuity and the creativity of the researchers, who are constantly pushing the boundaries of machine learning and developing new and improved algorithms.
Wow, we've really covered a lot of ground in our deep dive into gradient descent.
Yeah,
I mean, from the basic concept to all these different variations and challenges. It's been quite a journey.
It really has, yeah. We started by kind of, demystifying gradient descent and showing, how it helps us find those best parameters for our machine learning model.
Right.
By minimizing, that cost function that we talked about.
Right. And we've delved into some of those, those finer points like learning rates and local minima and even those vanishing and exploding gradients. And then even, the techniques for how to address those challenges.
Yeah, it's definitely a lot to take in, but hopefully our listener, has a solid understanding now of this really fundamental concept that powers, so much of machine learning today.
I think we've done a good job of that. So before we wrap up, what are some key takeaways? What do you want our listener to remember about gradient descent?
I think the most important thing is just to understand that gradient descent, despite all its complexities, it's a remarkably intuitive and powerful algorithm. It's all about iteratively improving a model by taking these small steps in the direction that reduces the error.
And it's also crucial to remember, that there are so many different flavors of gradient descent out there, each with their own strengths and weaknesses. So choosing the right variant can really have a big impact on the efficiency and the effectiveness of your model training.
Right.
And while we didn't get into too much technical detail, I think it's helpful to be aware of those those potential challenges, like those vanishing and exploding gradients. But thankfully, there are tools and techniques to kind of mitigate those issues as well.
So I think this deep dive has really provided a great foundation for anyone who wants to delve further into the world of machine learning. It's just amazing how such a seemingly like simple concept can be so versatile and so powerful.
Absolutely, yeah. And it's just it's just the tip of the iceberg. The field of machine learning is constantly evolving, with researchers developing new and improved algorithms all the time.
So to our listener, keep exploring, keep learning, and keep asking questions. There's a whole universe of knowledge out there, and gradient descent is a great starting point for unlocking its secrets. Well said. And until next time, happy exploring.